In section 12.5, we learn how to expand a binomial, like x plus y, when it's raised to a power using a shortcut called the Binomial Theorem. PreCalculus Online starts now. In section 12.5, we study the Binomial Theorem. And to do that, we first need to talk about combinations. And to do combinations, we first need to review factorials. So remember what factorials are. If we have n factorial, then this is equal to n times n minus 1 times n minus 2 all the way down to 2 times 1. So it's the product of every positive integer less than or equal to n itself. Now we talk about combinations, and combinations are also called binomial coefficients. And the reason for that is this very section. We're going to use these to come up with the coefficients when we expand binomials. And the symbol for that is this. It's n choose j. It has to have the parentheses. It looks like a fraction, but there's no bar in the middle. And this is read as n choose j. And technically what this is the number of ways to choose j items from a set of n different items if the order of the items chosen is not relevant. So, for example, if you wanted to choose 5 members of your basketball team out of 9 different players, that would be 9 choose 5. You have 9 players to choose from, and you choose 5. But if I make the question more specific and I say, suppose you have 9 players, you need to choose 2 guards and 3 forwards, then it becomes a little too specific, and the order in which you choose them matters because the choice of a forward might be different than the choice of a guard and things like this. Then this is not a combination and you can't use the choose. This is a more general type problem called the multiplication principle or a permutation. So order does not matter. And for this section, the order is not going to matter. That's just a general overview. Now the formula for a combination, n choose j, is n factorial divided by j factorial times n minus j factorial. And what you're going to see here is that the numerator is going to be the number of items that you have to choose from, and the denominator is going to be 2 numbers that sum up to n, the top number that you're taking the factorial of. Let's look at some examples. Example number 1. Find 4 choose 3. So 4 choose 3 would be 4 factorial divided by 3 factorial, and then I'll go ahead and do this the long way, times 4 minus 3 factorial. But if I simplify just that one piece at the bottom, you get 4 factorial times 3 factorial times 1 factorial. What I want you to notice is that whatever numbers you're choosing here, they must always add up to n. So a lot of times we'll just skip the part with the subtraction, unless we're doing something with the definition or something, but we'll skip that part and then just say, well, if we had 3, then what else do I need to make 4? Well, I needed a 1, and so that's where the 1 comes into place. So 4 factorial would be 4 times 3 times 2 times 1. 3 factorial would be 3 times 2 times 1, and 1 factorial is 1. Let's cancel what we can. So 3's, 2's, and 1's cancel, and you get 4. There's a 1 in the bottom, but 4 divided by 1 is just 4. So 4 choose 3 is in fact 4. Let's look at part B, 6 choose 2. So this would be 6 factorial divided by 2 factorial times 4 factorial. And this is going to be 6 times 5 times 4 times 3 times 2 times 1 divided by 2 factorial is 2 times 1, and 4 factorial is 4 times 3 times 2 times 1. Let's go ahead and cancel 4's, 3's, 2's, and 1's. And then we can cancel a little bit over here. The 2 and the 6 reduce down to 3. So we get 3 times 5, which is 15. So 6 choose 2 is 15. Now something interesting that must happen, which doesn't necessarily seem like it should, but it must always happen, is even though you're using a fraction, everything in the denominator has to cancel. And the reason for that is because these combinations are talking about arrangements of things. You're choosing j items out of a set of n things. And if you're going to do that, you have to end up with an integer, right? You have to end up with a countable number of these things, and it's countable with the integers, because I can then count them 1, 2, 3, 4, all the way up to the last one. And so we must end up with an integer here. Let's do a little short proof here. Show that n choose 0 is equal to n choose n, which is equal to 1. Well, I'll just do the n choose 0 is equal to 1 first. So n choose 0 would be n factorial divided by 0 factorial times n factorial. Recall that 0 factorial is actually equal to 1, because the question that you're answering there is, how many ways can you arrange 0 items in a row? And the answer is there's only one way to arrange 0 items in a row. It's sort of the empty arrangement. There's nothing there. And so there's one way for that. So then we have n factorial over n factorial, which is 1. Similarly, let's go with n choose n and show that that's equal to 1. So using the definition, this would be n factorial over n factorial times n, the top number, minus n, the bottom number, factorial. That gives me n factorial over n factorial. N minus n is 0, so that's 0 factorial. And this, just like above, cancels to be 1. So the moral of this story is that anytime you have n items and you choose 0 of them, there's one way to do that. You haven't chosen anything. Or if you have n items and you choose all n items, there's only one way to do that as well. You just choose them all. That's the one way you can do that. Example 3. Show that n choose j is equivalent to n choose n minus j. All right, to do this one, we're going to start with the left side, n choose j, and we want to end up with the right side. Now, to help us do this little proof, it would be nice to know what the right side actually works out to be. So I'll know when I have the right side whenever I can expand into this. N factorial on the top. Then, using the bottom term here, it would be n minus j factorial times, and then I need to get it to be n minus j factorial. Because remember, the format of a factorial and a combination, rather, is that you have n minus the number that's on the bottom. So let's see if we can work this out to get that. By definition, n choose j factorial would be n factorial divided by j factorial times n minus j factorial. And if we just do sort of a rudimentary check here, I notice I've got my n factorial on the top. I've got my n minus j factorial. So the part that I need to finesse is the j, and I need to turn it into n minus j factorial. Well, that's actually easy to do. We'll have n factorial over, let me move the term on the right to the left side here, n minus j factorial, times, and then what is j equal to? Well, j is equal to n minus n plus j. Here I've just added and subtracted an n from inside here. I forgot my factorial over here. I had the factorial symbol there. Now, what is n minus n plus j? Well, I can actually do some grouping and factor out a negative. So I'm going to take the first n here, minus, and then I'm going to factor out a negative from these two terms here. That's going to leave me with n, because the negative came out. It was a positive j, factor out the negative, it becomes minus j, and voila, there it is. And that's exactly what I was looking for. So this is equal to n, choose n minus j. Now what does this one tell us? Well, this one tells us that, say for example, suppose I choose 7, choose 3. Then I know that that's going to be the same as 7, choose 4, because these two numbers here add up to be the number n. Similarly, if I had 20, choose 13, then this would be the same as 20, choose 7. Because if the bottom two numbers add up to the top number, then they must have equivalent combinations. Our next topic is Pascal's Triangle. Pascal's Triangle is basically built up in the following fashion. First off, there's going to be ones going along the sides. And then, in order to get sort of the middle numbers, what you do is you take two numbers in the same row next to each other, you add them together to get the row number that's in the middle on the next row down. So here 1 and 1 is 2, 1 and 4 is 5, 6 and 4 is 10, 10 and 10 is 20, etc. So that's the pattern that repeats. You add two numbers from above that are consecutive, and they form the new numbers below them. Next, the rows are numbered, and we start with row 0, followed by row 1, and then row 2, row 3, etc. And the row numbers can be found in this sort of secondary diagonal, not the ones, but then going down here, 1, 2, 3, 4, 5, etc. So those are the row numbers. Now, the remarkable thing about this, and the reason why we're studying this, is because each of the numbers in Pascal's triangle is a binomial coefficient. It's actually in the form of n choose j. The binomial coefficient is in the form of the row number on top, and then the entry going from left to right, starting with 0, 1, 2, all the way up to n itself. So for example, suppose we wanted to know what 4 choose 2 was, and we wanted to use Pascal's triangle instead. Well, the first thing we would do is we would go to row 4, and then the numbers in row 4 are the 0 number, the 1 number, the 2 number, the 3 number, and the 4 number. And so 4 choose 2 is 6. Let's verify. 4 choose 2 should be 4 factorial over 2 factorial times 2 factorial, which would be 4 times 3 times 2 times 1 over 2 times 1, 2 times 1. The 2 and the 1 cancel, and then 12 divided by 2 is 6, indeed. So one way to easily produce these binomial coefficients is just to produce Pascal's triangle. It's practical up to about row 6, as you see here, maybe even row 7 or 8, but it just sort of depends on your application. And now, the binomial theorem. This is probably one of the greatest theorems that we'll do in pre-calculus the whole semester. Basically what it says is that if you have a binomial, which is in the form of x plus y, and you raise it to a positive integer n, then you can produce the result without having to do all the little FOILs so many times, right? Because it just gets unwieldy. But you can produce that because it's going to be this sum here. The sum is j goes from 0 to n of n choose j times x to the n minus j times y to the j. So a couple of things to notice here. The powers are n choose j and j, so these add up to n. And remember that we're doing n choose j, but we've already showed that n choose j is the same as n choose n minus j. So you can sort of mix and match these binomial coefficients because they're going to be the same regardless of whether you're indexing with the x or the y, and they are symmetric. Now remember also that you can use the binomial coefficients that come from Pascal's triangle. Let me show you how this works. Example number 4. Expand x plus 3 squared the old-fashioned way. Let's go ahead and do that. So x plus 3 squared would be x plus 3 times x plus 3. And so we're going to get x and x, which is x squared, 3x and 3x, and then finally 3 times 3, which is 9. So this simplifies to x squared plus 6x plus 9. So that wasn't too bad. But now imagine if you had to do x plus 3 to the 7th power. That could get a little out of hand. Now, how would I demonstrate this with Pascal's triangle and the binomial theorem? So x plus 3 squared. Well, first I would recognize this as the sum as j goes from 0 to 2, which is the power, of 2 choose j times x to the 2 minus j times 3 to the j power. So all I've done is sort of substitute the elements that I had from here. The y turned out to be a 3, and the n was the power, which goes in these 4 spots, and that's the 2. Now let's go ahead and work this out. This sum would be 2 choose 0 times x to the 2 minus 0 times 3 to the 0 plus, and that was the j equals 0 term. Next I'm going to do the j equals 1 term, which would be 2 choose 1 times x to the 2 minus 1 times 3 to the 1 plus, now I'll do the j equals 2 term, 2 choose 2 times x to the 2 minus 2 times 3 squared. Two choose 0. Now how do I get 2 choose 0? Well, I can produce a little Pascal's triangle right here. 1, 1, 1, 1, 2, 1. So it's going to be this. So the first term is a 1. 2 choose 0 is 1. Times x to the 2 minus 0 is just x squared. And then 3 to the 0 is equal to 1. Plus 2 to the 2 choose 1 is 2. X to the 2 minus 1 is x. Times 3 to the 1, which is 3. Plus 2 choose 2 is that final one right here. X to the 0 power times 3 squared. And then if you simplify that, you get x squared. 2 times 3 is 6. 6x. 3 squared is 9. 9 times 1 is 9. There it is. Now that was a lot of work for the one that we did, but that was merely for demonstration purposes. Suppose you had a longer one or a harder one, you'll see the value of that, especially in example number 5. Expand x minus 5 to the 4th power. So to do x minus 5 to the 4th power, we need to produce the row in Pascal's triangle that had 1, 4 at the beginning. That is 1, 4, 6, 4, 1. Again, you can just on the fly sort of create Pascal's triangle if you don't have it memorized. Now, another way that we can think about this is what substitutions should we make? Well, the x should just be x because that's the first one here. But the y from the binomial theorem above is actually going to equal -5. So here's how you can sort of create this polynomial on the fly. We're going to have a coefficient for the first term, and then we're going to have x to the largest power available, which is 4, and then we'll have -5 to the sort of complement power. Complement in this sense being a complement to 4 because that's the power. So what number plus 4 makes 4? 0. Plus, then we'll have another blank that we'll fill in here in a second. And then this would be x cubed -5 to the first. Again, we go down by 1 power and up by 1 power on the other one. Next, we have a blank. It'll be x squared times -5 squared plus blank x to the first times -5 cubed plus blank x to the 0 -5 to the 4th power. And then what goes in these blanks? Those are just the binomial coefficients. 1, 4, 6, 4, 1. So again, the powers on the x's, they went down as we went across. And then the powers on the -5, they went up as we went across. And so what do we have? 1 times x to the 4th times -5 to the 0 is just x to the 4th. Plus 4 times -5 is -20 times x cubed. Plus 6 times -5 squared. -5 squared is 25 times 6 is 150 x squared. Plus 4 times x times -5 to the 3rd power. -5 to the 3rd power is -125. -125 times 4 is -500. And then lastly, -5 to the 4th power is 625. And there it is. Much easier than having to write out x minus 5 4 times, carrying out the FOIL and then with the cubes and all that multiple times. Example 6. Expand 2x minus 7y to the 3rd power. So again, we need to pull up Pascal's triangle here. So it'll be 1, 3, 3, 1. And this is going to be blank. Now this time, our first term is 2x, and our second term is -7y. So this is going to be 2x cubed, -7y to the 0, plus blank, 2x squared times negative 7y to the first plus blank 2x to the first times negative 7y squared plus blank 2x to the 0 times negative 7y cubed. Pascal's triangle numbers, the binomial coefficients, go into place. And then we just have to work all this out. So 1 times 2x cubed times negative 7y to the 0, that's just 8x cubed. Next, 3 times 2x squared times negative 7y to the first, that's negative 84x squared y. Next, 3 times 2x to the first times negative 7y squared, that's going to be positive 294xy squared. And lastly, 1 times 2x to the 0 times negative 7y cubed. That's going to be negative 343y cubed. So you may have to do some arithmetic there, but still, it's much easier and less error prone than doing it the old way where you just expand and multiply. Lastly, find the coefficient of the x cubed term in the binomial expansion of x plus 2 to the fifth. So we're looking for the coefficient. I know that I need the x cubed term. So what does that mean the 2 is going to have as a power? Well, the 3 and this other power that I need must add up to 5. So it's going to have to be the 2 power. And then also, I know that this is going to be the binomial coefficient 5 choose 3, or 5 choose 2, either way. Remember, those are the same. So it'll be 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. The 2's cancel, the 3's cancel, the 2 and the 4 cancel and leave a 2 on the top. So it's 5 times 2 is 10. So this would be 10. But now the coefficient includes this 2 times 2. So the answer is actually 40.